We're going to look at the third example of evaluating indefinite integrals using the U sub or substitution method. Remember, if you can do it by another method, by a simpler method, then you should. But we get problems like this where we have the product x times the square root of 5x minus 3, and there's no, as I've said before, there's no product rule, there's no quotient rule for taking antiderivatives. The first thing we're going to do with this one is to put it in a slightly different form. It will help us to get rid of the radical and use a rational exponent. So now we have to look for, is there a composition in there somewhere? And if you say yes, 5x minus 3 to the 1/2 is a composition, you'd be right, it is. Now if we look at the inner function, 5x minus 3, we see that the derivative of that is 5, which doesn't exactly match up with the x. It's on the outside there. So you might think at first glance that this is not going to work because we need the product of a composition and the derivative of the inner function, and that's not quite matching up here. But we're going to introduce some clever algebra. All right, so one more thing I'm going to do here before I display the answer is I'm just going to put this in a different order so that I have my composition first and then times the x dx. So there's my composition times x dx. All right, so think about it for a minute. You could pause, and then I'm going to put the answer on. So here it comes. All right, so let's look at what's going on here. I am going to use 5x minus 3 to the 1/2. That is my composition. So the inner part is going to be u. So u is 5x minus 3. And the derivative of that is 5. Okay, we know that this isn't going to exactly get us where we want to go, but we're going to do some more stuff to make it all work. So f of u is going to be u to the 1/2. So let's look at what we've got. We can replace 5x minus 3 to the 1/2 with u to the 1/2. That's great. That's the first part of a substitution. But then we end up with an x dx there. Now let's go back and look here. Since du is equal to 5 dx, but we only have 1 dx, what happens if we just take that little equation, du is equal to 5 dx, divide both sides by 5, we get 1/5 of a du is equal to dx. So now we can replace that dx with 1/5 du. All right, so little by little we're getting rid of the x's, but we still have that x that's being multiplied in there. So now let's go take a look. Up at the top we have where we had u is equal to 5x minus 3. Notice that's an equation. We could solve it for x. So x is equal to 1/5 times u plus 3. All right, so let's go back to our integral. Now the first thing I did here was I removed that constant 1/5. And now I'm going to replace the x with 1/5 u plus 3. Right there is where you go. So now I have an expression which is totally in terms of u. I've gotten rid of all my x's by legitimate calculus and algebraic means. I've got a 1/5 in there. Another 1/5 is a constant, so I can move that 1/5 to the outside. So 1/5 times 1/5 gives me 1/25. Now I'm also at the same time going to distribute that u to the 1/2. So I multiplied u to the 1/2 times u and u to the 1/2 times 3, so I can simplify. And now that leaves me in a position where I can go ahead and take the antiderivative. So u to the 3/2, the antiderivative of that, remember, would be u to the 5/2 divided by 5/2, which gives you 2/5 u to the 5/2. And the antiderivative of 3u to the 1/2. So I've got to add 1 to my exponent, so 1/2 becomes 3/2, and then I divide everything by that new exponent. So I'm dividing by 3/2, and if you simplify that, you get 2u to the 3/2 plus, of course, your arbitrary constant. And now I need to return to an expression that has the x's in it. I want to get rid of my u's. I want to back substitute. So I'm going to substitute in the 5x minus 3 wherever I had a u, and I'm